Okay, so in this case, I just shared one document where it's like step by step few things that I will go through. So let me know if you were able to get that file. That's the EDNA for fungal genomes, which would be this one here. So here I'm explaining how I've been running EDNA for fungi, and in order to be able to run today, I have also another folder. So John has his folder of bacterial. I have my folder for fungi, which means like people doesn't get confused among two different approaches. So this approach, if you see here, I'm just explaining here, and I'll be using not a fungal. In this case, I'll be using an oomycete, which is Pythium ultimum. So this would be like eukaryotic genomes. But if you click on this folder, which everyone should have it, and it's gonna take you to all the files we're gonna need. So I have this is a Word document in Windows. So I'm gonna just switch to Linux. So this would be the file. Same file. So if you do control click on this one, it's going to take you to the folder, and then you have to download all of these to a folder that you have. So the ones that we need, since you already have Blast Plus installed, would be this one, which is the script. And these are the eProbe databases, like Puccinia database with 80 base pairs, Ramorum database with 80 base pairs, and Ultimum database with 80 base pairs. And also we have Ultimum real.fna is a FASTA file for the output from 454. Same for Ramorum, and same for Puccinia. So I have all those databases, but we won't be able to run through all of those. I'll be running only Ultimum, so you don't have to download all of those. And in this case, what I'm going to do is create here a new folder, which is called EDNA, and it's in the desktop. And I'm going to just download these ones. So just save file. And I guess you have to, everyone has to do that. And since we're using Ultimum eProbes, so it's going to be ult80.fasta. So we're going to download that one too. Save file. And the same thing for the real FNA, which would be the FASTA file from the 454. This is going to ask you to scan for viruses because it's a big file, I guess, 58 million bytes. So I just have downloaded anyway because I trust myself. And then download those. So I guess those are going to be in the downloaded folder, which are these ones, okay? So these three files are the ones that we need now. So what I'm going to do after I download them, I just cut and go to the desktop where I have my EDNA one. And this is empty, okay? So I just paste them there. And I'm going to have just three files now. So this is going to be the eProbes, and this is all you need in this case, eProbes, and these are the sequencing output. So now I can go ahead, and I was trying this before. Let's say I start from zero from the terminal. So I open a new terminal, and it's going to open, you can know which directory you are in with CWD, which is present working directory. I'm going to be on home, and my computer name. So usually what I will do is like I have to go to desktop. In my case, I don't know how you have it set up for you. And then I have in desktop, I have EDNA. And then I go to that folder, and now I can list whatever I have there. And I'm listing these by date. So I have here the three files. This would be the sequencing output. This would be the eProbe database. And this would be the EDNA one, well, this is just a name I'm using because I have different versions, but this is the latest version I did. Well, now we're going to run, as everyone did, we're going to run a blast. And we are using blast, so we can go here to the file I just sent you. And here is the, well, as John mentioned before, we have to first make the format the database. So it formats the database to be able to do the blast. So this is the command, so you can copy and paste it if you open this file directly on VirtualBox. But if you open this file in Windows, you have to activate Share Clipboard Host to Guest, okay? Which would allow you to copy and paste from Windows to VirtualBox. But since I opened this file here, I'm gonna go ahead and copy and paste it there. So you just copy and paste it here. I'm already in my directory I'm gonna work. So it's here. So I'm gonna go through this one. This is the command for make the blast database. This is the input, which would be the output from the sequencer, and this is the output file that you wanna call it. So it's gonna be the same one, but .dv. And they ask you for the database type, which is nucleic acid. You might have also databases from protein, but in this case we're not using proteins for EDNA. So you just run that one. This is error. You have to run that one to be able to have a formatted database. How it's showing some error application. So let me know if you're having the same error. I just ran it previously and it worked perfectly, but I was showing some error. Dash in would be the ult real. That would be dash out, right? Dash out ult real.tv. Okay, perfect. Now it's running. I think if you copy and paste, it's copying some blanks. So now it's formatted as John did. So now we can run blast. And blast, usually since I usually have like lots of EPROBs. But in this case, I reduced the number of EPROBs to 10,000 to be able to fit into the time. But probably we're out of time. But I'm going to run it anyways. And I'll show you the output because I have some outputs from you if it doesn't work. So in the same file I'll send you, I have this one, which is the blast step. Whenever you have the formatted database, you can copy and paste this one. So in this case, what we are doing, we are calling blast nucleotide. The task is blast n. The database, this is the formatted database you just created. So in this case, you just delete this one and you put what you just created. Ult real, and then it's going to be that database, .dv, not .fna, which was the previous one. The query is the FASTA file. In this case, it's ult because of ultimum, and it's 80, and it's a FASTA file too. And then the out is the desired output name. Usually what I use is, whenever I'm doing alt, I use alt for the database dash alt 80. So it's ultimum versus ultimum 80, and this is that text, and this is just the number of threads you're using, and the word size is 11, what works best for me whenever I was using EDNA. So if I hit enter, it's supposed to do the alignment. So now it's working. So in this case, since we have 10,000 EPROBs, it's going to take probably 7 minutes for this one to finish. So meanwhile, I'll show you some outputs that I have already in my document here. And this is a previous folder I just created. So what you will get from that one would be a versus ult 80. Okay, so this would be similar. I'm doing here I did here ultimum versus ultimum probes 80, and this is part 1, and this is the alignment, ultimum versus ultimum, and this is the one that I'm gonna get now, the output from the blast. This is a previous one that I already did, so I'm just gonna open it and just to show you. Okay, what's working? Well, another way to check if this one doesn't work, you can always open a new terminal. And while you're running the other terminal, you go to the working directory, which would be EDNA. And in this case, you list what you have, because now it should be creating a new file, which is this one, ultimum 80.text. So you can check that text file using nano, which is ult-ult.text. It should be easier to check. So here we have like the output that Blast is creating now. It's not done yet, but we can check the previous data here. These are normal alignments we would make in like ncbi.com, but in this case we are using our own database, EPROB database, and our own sequencing output. So this is what we're getting, but if we go through all these for 10,000 EPROBs and for 140,000 reads, this is going to take you forever. So the most important thing is the EDNA parsing. You can exit from this with Control X. So, and this is one terminal I have. The other terminal is here, still running. Like, we're having problems here. Okay, here, open. Whenever you open in the same thing in gedit, it's gonna become very slow, so it's not recommended to open it that way. It's better to open via nano. So I'm gonna close it because it's gonna get so slow. So now this one is still working, but meanwhile this works, it's gonna take around 10 minutes. After this one is done, which is the blast step, we're gonna have a desired output name. We're going to have a desired output text file, which is the blast that I was just showing you. So if I would have the whole database, the whole EPROB database, it would take me approximately 1 hour. So I just reduced it to 10,000 EPROBs, and now it will take around 10 minutes. So after that, whenever I get that output, what I can do is run. In this case, this would be EDNA. The EDNA file for fungal, and this is a 2.0 version where we have the output file from the blast, and then this is a space. This is programmed by Shift for those who know how to program in Perl, and then this is going to be the desired output name with the part, which are going to be the part ones, and this is the e-value space one space here, and this is the value, 10 to the negative 9. I can be this stringent because I have multiple EPROBs as opposed to bacterial or viruses, which like there are lower number of EPROBs. So after this, we're still running here. Whenever we have this thing blinking here, it means that it's still running. So we have to let it stand there longer. But if you're doing this in your computer, after a certain time of 10 minutes, it's going to be done. So you'll have the output file. Let me walk you through the output that I would get if I do the parsing step. So after I do this step, if I run this Perl script, since you have Perl and BioPerl installed, you're going to have this output, which is going to be called parse. It depends how you name it, but you have to name it differently from this one. So this is going to be called parse. So I have a document that is already done because it's going to take a little longer for fungi. So in this case, two files are created. This is one file is called parse, which will have all the row alignment statistics, and this is a tab delimited file, which will give you even the ones that have 0 hits and 0 matches. So most often, if you just want some more user-friendly one, this is the one that has the high scoring matches. So this is the one we should go after we have the parsing step, and this is easier to open because it's not that big file. So in this case, I'm going to do Control Home. So we have different, and I have enumerated these. These are the number of EPROB, number 1, number 3, number 4, number 5. This is how many EPROBs I have. Like this is the EPROB number 3, up to 10,000. Okay. We haven't named each EPROB yet, but we have an EPROB depth that, as I mentioned before, and I accept only EPROB depths that are only higher than 2 or higher than 4x. For instance, in this case, this EPROB, which is called sequence 2, it has an EPROB depth of 227, so which means that it has been assigned to 227 reads with an E-value and this is an average E-value of 5 to the negative 29, which is smaller than 10 to the negative 9. And these are just non-HSP and significant hits. So these are the ones that we want to know. 273 high-quality matches for this EPROB. Okay? So whenever we go to the end, and we can go to the end of this file with Control End, we're going to have the output. John already showed you a similar file. In this case, I'm using high-quality matches. So the number of EPROBs, as I already mentioned, I reduced to 10,000 because of time, because usually it will take 1 hour. And here I'm just calling them high-scoring segment matches. There are two types. These are the ones that we have to focus in, which would be the high-quality matches. These are considering other hits that are not high-quality matches. So in this case, out of these ones, we get only 3,834 high-quality matches. So this will tell us if it's positive or it's negative. Similarly to Megan, in Megan it will tell you the number of reads, but the number of reads it's not telling you like either. It won't tell you the depth of that alignment or anything, or doesn't have any quality check. So after all the quality checks, we have around 3,000 high-quality matches. So after you have this, you can compare it, which will be easier to compare it with this table that we have here. And in this case, we are using PQ Multimum. And as I mentioned during my talk, PQ Multimum, if you would have less than 5 or 5, it would be a doubtful diagnosis, which means you don't know if it's either positive or negative, because this sequencing is random. So you might pick or might not pick the pathogen. Or it might be other eukaryotic reads hidden here. So since we have way higher than 5, in this case comparing it with 5 would be in this case would be 3,000, it's highly likely this is positive. I would call it like very positive in this case. So similar. Okay, so let me go back and check if it's done. So in this case, it's done, and I would have the same file here I was showing you. So if I go to the desktop, I have EDNA here. Close this one. And I have the EDNA here. And if I put to list one and by modified time, it was just done, and it has 328 million bytes. This is the output from BLAST that I was just showing you, okay? And then after that, you just have to run the parsing step, and I'm just gonna leave it running. Probably some of you finished if you are following it now, but you just have to copy and paste this one and modify it, which would be here. And here is the e-value. Don't forget the e-value here, because if you don't put that e-value, it's gonna show you an error. So in this case, this is the script per new parser species, and then this is the output from BLAST. The output from BLAST in this case would be ultimum, and I think ultimum, that text. And the desired output file from this parsing would be the same, probably ult8, and then I just put #parse. And then if you run that one, it shouldn't give any error, and it's gonna run for 10 minutes. And then we're gonna have that file that I was just showing you.
Andres, is there a way you can enlarge the text in your Ubuntu?
Large text.
Excuse me a minute. If you go to the View option in your menu and you say to, let me try it. The word is Adjust Shared Application, and you want to click Actual Size, and that'll make the text bigger.
That made them bigger.
Yes.
Okay. So this is still running. This is the parsing step, so it's gonna take 10 more minutes. In this case, it's gonna end up showing you a file that I just showed you. And this is the desktop EDNA. So let me show you that file. I just want to show you to compare what happens, and this to finish this portion. I just want you to share what I already have, because it's gonna take longer if we do that one. But here I have a prior run that I did. So I did also another run whenever I was here. You can see this is a BLAST output from Ultimum database against a Puccinia 80 base pairs, that text. In this case, I'm trying to detect if there's Puccinia in the database. So it should give me 0 or something lower than 1. 1 if I'm not wrong. These are just the raw data, which means like within zeros, I think. And this would be the high scoring one. So this is the Ultimum database Puccinia 80 parse text high scoring. I told you will get 2 files, and the high scoring are the ones that you want to focus on. So in this case, you have number of prof 10,000. High scoring segment matches, which are the high quality matches, 0. And if you go to the file I sent you, if you get at least 1 for Puccinia graminis, you might say this is doubtful. But as since you got 0, it means that there's nothing like there's no Puccinia graminis in that database. So this is very stringent thing. 1 is very stringent. Even though it's very stringent for 1, we have 0, and you can test all the EPROB sets that I sent you in that Google Drive folder against Ultimum, and it should show, let's say for Phacophthora phacaraceae, it should show something lower than 100. For Phytophthora arboreum, it should show something lower than 25. And these are only 10,000 EPROBs. So we can call it negative for Puccinia graminis, but we can call it positive for Pythium ultimum after we check that output. And now in my terminal it is still running, but I just showed you all the tentative outputs you might get. And just to that we are getting the same thing that I just showed you, I'm gonna move to. You see here I'm organizing the data, I'm sorting the data by date. And in this case I have this one was updated at 1:56 p.m. So these are the high scoring ones. So I can just go ahead and check this one, how is it going with Nano and Ultimum, and then Ultimum 80 parse that text. And this is gonna be raw data if I put that text. Oh, well, that text that high scoring. And that text. Sorry, there's a typo there. So it will show me a previous view of what I'm getting. And again, I'm getting the same thing as I showed you in my other folder. So this is not going to show the whole thing because it is still working, and at the end it's going to print the final version. So it's going to take a little bit more, probably 5 more minutes. And then Control X to exit, and if it asks you to save, that means that you moved something there, so you don't save it. That would be what I have for now. So that's the way you can be able to discriminate among 2 fungal or eukaryotic organisms with high quality matches. Just let me know if you have questions about it or if you are stuck in some steps.